Hello everyone, I'm Chen Yun and I'm happy to present our work from UMass Amherst on how well Clip understands texture. Our work is focused on zero-shot learning capabilities of Clip on textures based on two motivations. Firstly, textures are useful for describing object categories, especially in fine-grained domains. Secondly, the vocabulary for describing textures are rich and unique, so it's worth looking into whether the models like Clip can work well on the domain of textures. We present our analysis in three parts. The first is zero-shot classification of textures. The second is associating textures with natural language phrases. And the third one is recognizing textures on bird images. For the first part, we apply zero-shot classification with Clip on 4 texture classification datasets. We report per image accuracy on different variants of Clip, as shown in the table, and we can see that the variants with transformer backbones are better than ResNet backbones. The best model is the last one, which is trained on larger images than other models in the table. We also experimented with different prompts as listed in the table. We compare the basic versus the large version of the transformer backbone and show that the basic version has larger variance in performance across prompts. So we conclude that larger models are more robust to prompt changes. For the second part, we study textures with natural language phrases. We use the DTD2 dataset, which has texture images and open vocabulary descriptions of the textures. We compare Clip with DTML, which is a strong baseline from metric learning trained on DTD2 dataset. We have two tasks, phrase retrieval, which given an image and rank all the texture phrases, and the image retrieval, which is given a phrase and rank all the texture images. We can see that Clip performs similarly with the baseline in image retrieval, but is slightly worse on phrase retrieval. We then further look into the best and worst performing attributes in image retrieval on both models. We can see that the two models are both good at common colors and patterns, such as white, black, soft. On the other hand, Clip is better at relatively rare colors such as orange, pink, purple, and rare materials such as wood, marble, and glass, while Clip is worse at words that are only frequent in DTD2 but rare in the more open-ended vocabulary like lined, bumpy, and rough. For the third part, we extend our experiments on natural images in the fine-grained domain of birds, namely the CUP dataset, which is a fine-grained bird dataset with localized attributes on body parts. So the attributes include colors like red and gray and patterns like solid or spotted. We conduct a zero-shot phrase and image retrieval on texture attributes with both models. So as shown in the table, we can see that Clip is better on image retrieval than the DTML baseline, but their performance are similar on phrase retrieval. We further improve Clip classification accuracy by adding localized texture attributes to the prompts. And we find it especially effective when using scientific species names rather than common names of birds to fill into the prompt. So we also show two examples here, which are two very similar species, but we can tell their difference from the texture attribute descriptions. To conclude, we find Clip achieves strong zero-shot performance for not only texture classification and texture image and phrase retrieval, but also understanding textures on natural images of birds. Additionally, we find it effective to add texture attributes to prompts to help zero-shot classification. This is the end of our presentation, and thank you for your attention.